Welcome to the next lecture of transistor series. So here we'll be exploring the common base configurations in detail. Now start with the symbol of the transistor. Let us have a review on it. So this is for PNP transistor and NPN transistor, and we have seen that if we want to use this transistor in a circuit, then we can have three different types of configurations. So in our previous lecture we have seen that there are three types of configurations: common base configuration, common emitter configuration, and common collector configuration. So in this lecture we are going to elaborate common base configuration. So if we have look at this diagram, so for NPN and PNP transistor, the common base configuration is shown, and here we provide the input signal and from here we take output. So this is basically our input section and this is the output section. So now to elaborate this one, we are going to consider some parameters associated with the common base configuration. So first is the current amplification factor. So current amplification factor in common base configuration is denoted by alpha, and alpha is defined as the change in the collector current for a change in the emitter current, keeping the VCB constant. So that is how alpha is defined. However, many times we consider only the DC values of the collector current and emitter current. So in that case we can write alpha DC is equal to IC by IE. This is much more popularly used, and it is quite evident. We have seen that collector current is always less than the emitter current. So as a result of that, alpha is always less than unity. Typically alpha is ranging between 0.9 to 0.99. So that is the typical range of alpha. So this is what is called current amplification factor for the common base configuration. Now in the common base configuration, we have seen that the collector base junction is in reverse bias. So under the reverse bias condition, if the emitter is open circuited, then the leakage current flowing from the collector to base is called the ICBO. This is the reverse saturation current. Just like diode in reverse bias, there is reverse saturation current. So here also in the transistor, when this base collector junction, here we are applying the reverse voltage, so we are getting some reverse current or leakage current or dark current, that we are calling as ICBO. So now if we have a look at the collector current under the common base configuration, then we can say that the part of emitter current which reaches to the collector terminal, that is alpha IE, that is constituting the IC. However, due to the leakage ICBO, that is also the part of the collector current. So as a result of that, we are getting actually IC is equal to alpha IE plus ICBO. So that is an interesting relation. In addition to that, earlier we have also seen that IE is equal to IC plus IB. So this is another relation. So now if alpha IE is much greater than ICBO, so under normal circumstances we have this relation, alpha IE is much greater than ICBO, and in that case we can write IC is equal to alpha IE only. So by ignoring ICBO in equation 1. So let us name it as relation number 3. So now if we substitute the value of IE in equation 1. So here if we substitute the value of IE, then we can write that IC, that is equal to alpha into IC plus IB plus ICBO. Further, if we expand it, we can write it like this: alpha IC plus alpha IB plus ICBO. So if I take it the other side and take IC common, then we can have 1 minus alpha into IC, that is equal to alpha IB plus ICBO. So this one if I take in the right hand side, then we can get the expression for the collector current IC, that is equal to alpha divided by 1 minus alpha into IB plus 1 by 1 minus alpha into ICBO. So call it equation number 4. So from this equation, what we can say that if we can control the base current, then we can control the collector current. So collector current or the output current can be controlled by controlling the IB base current or by controlling the emitter current. So that is an interesting relation for finding the collector current. Now further see this input and output section of common base configuration. So this is the same diagram that we have seen in the first slide. So just little differently I have drawn, and we have seen that input resistance and output resistance. So what are these? I will elaborate that in the next lecture. So for the time being, if we see this input section, and here if we put KVL, and in output section if we put KVL, then we can find the input and output equation for the common base configuration. So in input section, what we find that the input current is IE, and input voltage to this junction VBE. So this is the input voltage. Similarly, output voltage here in the transistor, there we can say that output voltage is VCB. We are not considering the load voltage. RC you can consider as load, and here we can also say that this is also the output voltage, but for the time being we are concentrating on the transistor part. So this part we are not considering at this moment of time. So our output voltage is VCB and the output current is IC. So these are the input and output parameters associated. Now if we apply the KVL to the input and output loop, what we can write that VEE that is equal to the drop across RE. So RE into IE plus this one VBE or VEB. So VBE or EB, anything you can write. So call it equation number 5. So up to equation number 4 we had in the previous slide. Now from the output section we can get the output equation as VCC. Applying KVL here, we can write VCC equal to drop across this IC into RC plus VCB. So this is the equation associated with the output section. So we end here our discussion, and in next lecture we'll see the input and output characteristics. So we'll pick up from here in the next lecture. Thank you.